Our discussion for today is all about the rates and orders of reactions. Now, to consider the processes of ADME, the rates of these processes have to be considered, and they can be characterized by two basic underlying concepts. Now, when we say rate of a reaction or process, it would refer to the velocity or how fast, how slow is the reaction. And for drugs, it can be either a zero order or a first order kinetics. So the rate of a reaction is determined experimentally by measuring the disappearance of drug A at given time intervals. So when we give the drug to a patient, we would expect that that certain drug will be eliminated from the body. And when we try to measure that, so we try to know the rate of it. Now, with regards to the order of the reaction, it is referring to the way in which the concentration of drugs or reactants influences the rate of a chemical reaction or processes. Now, there are two most common order of reaction. So that would be the zero order kinetics and the first order kinetics. Now, let's begin with the zero order reaction or kinetics. Consider the rate of elimination of drug A from the body. Now, the amount of this drug A, if it is decreasing at a constant rate, so when we say constant, the same amount, then that rate of elimination of this drug A can be described as dA over dt equals negative K asterisk, where K asterisk is the zero order rate constant. So to get this one, so the amount of drug over the time. Now the reaction proceeds at a constant rate and is independent of the concentration of drug A present in the body. So what does this mean? So when we say constant, that would refer to the same amount, no? Same amount that is eliminated. And this amount that is eliminated is independent of the concentration of drug A, meaning it does not, the concentration of drug A does not affect this constant rate that is being eliminated. So the amount of drug eliminated does not change with the amount of concentration of drug in the body. So kahit na ano pa yung amount ng drug A sa body, basta yung amount that is being eliminated is constant, pareho. But when we try to compute for the fraction, now the fraction varies because this fraction is computed as to how much is left, no, of the drug. Now, a very common example of zero order reaction is your ethyl alcohol. Now, there are other two drugs that is eliminated by zero order kinetics, and that is your phenytoin and your aspirin. Now, for drugs that show this type of elimination, now there will be accumulation of plasma levels of the drug, and when we try to graph that, it would be a nonlinear pharmacokinetics. So look at this table. For example, we give a 100 milligram drug to a patient, and this drug follows a zero order kinetics or elimination. So when we try to see how will it goes in the body, so we start with the 0 hour. So that time is in hours. Then the amount of drug that is given is in milligram. Then the amount of drug eliminated also in milligram. And then this is the fraction of drug eliminated. So at 0 hour, you give your patient 1,000 milligram of the drug. So nothing yet is eliminated. After 1 hour, there is only 850 that is left of the 1,000. So when we deduct 850 from 1,000, there is a 150 milligram that was eliminated. And this 150 milligram represents 15% or 0.15% of the 1,000. Now, another hour passes. So again, from the 850 that remains in the body after 1 hour, there will only be 700 after 2 hours. So again, 150 milligram has been eliminated. And this 150 represents 0.18 of the 850. Then another hour passes, another 150 is eliminated, bringing the concentration of the drug in the body to 550 milligram. And this 150 here represents 0.21 of the 700, and so on and so forth. So if you notice, the amount that has been eliminated from the body is the same, regardless of how much what that was left in the body. So even if you start with 1,000 or 850, still it is the same. So this is for the zero order. So constant yung amount in terms of the milligram. Now, it is independent of the concentration. Meaning, kahit ano pa yung concentration na naiwan, yung amount na ma-eliminate will always be the same. Now, the rate of the reaction of a zero order does not depend on the substrate. Now, as what we have seen in the table in the last slide, no? So, kahit na 850 na lang or 700 na lang yung natira, but then the amount that was eliminated is still 150. So given this formula, which I have presented in the previous slide, now if we try to extrapolate from this formula, we will get this new formula here. Now we will not go into the derivation or extrapolation. So I just want you to remember this formula and also this formula. Now, in this formula, the KO here represents the zero order rate constant in units of milligram per minute. So, and the AO is the amount of drug at time zero, meaning the initial amount that is being given to the patient. With regards to the half-life for a zero order, it is not constant. So when we say half-life, as I have always mentioned in our previous discussions, it refers to the time for a drug to reduce to 50% of its original concentration. So pag zero order, yung reaction, yung half-life is not constant, meaning it will vary from time to time. Now, this half-life is proportional to the initial amount or concentration of the drug, which is this one here, and inversely proportional to the zero order rate constant, this one. So T1 half here represents half-life, which is equal to 0.5 times the initial concentration of the drug at time 0 divided by the zero order rate constant. So please try to remember this formula for half-life for zero order reaction, because pag first order, it would be a different formula. First order reaction. Now, if the amount of drug A is decreasing at a rate that is proportional to the amount of drug A remaining in the body, then the rate of elimination of drug A can be described as D over A divided by dt equals negative Ka, where K stands for the first order rate constant. Now, with the extrapolation method, so we will get this formula here. The log Cp equals to the negative Kt over 2.3 plus the log of Cpo. Now, the negative sign denotes that the concentration is being decreased by elimination. When we go to the computation of problems, then I would explain this formula. No? What does this stands for later? Now, in the first order reaction, it will proceed at a rate that is dependent on the concentration of drug present in the body, meaning that the amount of drug present in the body has an effect on how will that reaction takes place. Now, it is assumed that the processes of ADME follow first order reactions and most drugs are eliminated in this manner. So there are only a few drugs that are eliminated by the zero order, but most of the drugs that we have are eliminated by the first order kinetics. The amount of drug administered during a dosing interval exactly replaces the amount of drug excreted. So when this equilibrium occurs, meaning the rate in equals the rate out or the drug administered equals the drug excreted, then we can have a steady state concentration. So when we say steady state, that would mean that the concentration of the drug in the body is already constant, meaning if we try to graph it, we will be seeing a constant or a straight line in the graph, no, horizontally. So this graph here is an example of a first order reaction. Now, when we graph, the y-axis is the dose or the amount, the concentration of the drug, while in the x-axis, we plot the time. So in this graph, at 0 hour, we give a 64 milligram per ml of the drug, and as time goes by, the amount of the drug decreases because um, part of the drug has already been eliminated. Okay, look at this table. Now again, so we have the time after administration measured in hours, the amount of drug in body in milligram, the amount of drug eliminated again in milligram, and the fraction. Now at 0 hour, we give a 1000 milligram drug. So nothing yet is eliminated. Now, after 1 hour, the 1000 becomes 880 milligram. So if we deduct 880 from the 1000, we would get a 120 milligram amount of drug that has been eliminated. So this 120 milligram that has been eliminated represents a 0.12 fraction or a 12% of the 1000 that was initially given. Now, after another hour again, the 880 becomes 774. So if we try to deduct 774 with the 880, the answer would be 106. So meaning 106 milligram is eliminated at the second hour. Computing 106 from the amount that was left, 880 milligram, we get a 0.12 fraction. Then another hour passes, the drug that remains in the body is only 681. So deducting it from 774, there is a 93 milligram drug eliminated. And this 93 here represents a 0.12 fraction of the 774. Another hour passes, or in the fourth hour, the 681 milligram becomes 599. So there is an 82 milligram amount of drug eliminated. And again, this 82 milligram here represents 0.12 of the 681. Again, in the fifth hour, the 527 remains. So there is a 72 milligram that was eliminated. And then another hour, the 527 becomes 464. So there is a 63 milligram amount that was eliminated, and so on and so forth. Now, looking at this table, we can say that the amount of drug that is being eliminated is dependent on the amount of drug that was left. So, beginning at 1,000, 120 yung na-eliminate. Naging 880 siya. Then, another hour passes, the 880 becomes 774. 106 yung na-eliminate. So kung titingnan natin, yung amount of drug na na-eliminate is hindi pareho. No? Hindi pareho. But we can try to see that when we compute it or in a fraction form or percentage form, this represents a constant fraction of drug eliminated. So from this, we can say that this drug, there is a 12% amount that is being eliminated every hour. So yun ang kaibahan ng first order reaction sa zero order. If you remember, sa zero order, yung amount ang pareho, yung fraction ang hindi. But with the first order, the amount varies because the amount is dependent of the fraction, of the amount that was left, and the fraction is the same. Okay. With regards to half-life, in the first order reaction, the half-life is constant. No? So for drugs that follow first order kinetics, yung half-life is constant, meaning yung time na nare-reduce yung drug in the body by 50% is constant, unlike dun sa zero order na hindi constant. So the formula to get the half-life of a drug undergoing first order kinetics is this one. T1 half or half-life equals 0.693 divided by the K or the first order rate constant. Now, this formula here, we can derive another formula, no? So, T1 half can also be computed using 0.693 multiplied with the volume of distribution of the drug divided by clearance. So if problems will be presented to you and the question is to look for the half-life, try to see what is being given. If the first order rate constant is given, then you can directly compute for the half-life using this formula. But when if K is not given, but rather the clearance and the volume of distribution is given, then we can use this formula because K is equal to volume of distribution divided by clearance. Now, we'll be discussing that in another topic, why is it that K is equal to volume of distribution divided by clearance. But for now, I want you to remember this half-life formula for first order. So, meron tayong dalawa. So, in the first order reaction, no matter what the initial amount or concentration of drug is there, the time required for the amount to decrease by 1/2 is constant. Kasi nga, di ba sabi natin, the half-life is constant. So, given this example, this drug has a half-life of 1 hour. So, we started with 100 milligram. Then after 1 hour, it becomes 50. So, 1/2. It was reduced to 1/2. Now, another 1 hour passes. So, this 50 here becomes 25. And this 25 becomes 12.5 and so on and so forth. So, looking at this, we can see that the half-life is constant because every hour, the drug is reduced to 50%. Okay. Let us try to differentiate a zero-order reaction with a first-order reaction. So, in terms of the amount that is eliminated, sa zero-order reaction, constant yung amount ng drug na na-eliminate. Whereas sa first-order, the amount of drug eliminated is dependent on the concentration of the drug in the body. So, this would depend, as you have seen in the previous slides. With regards to the rate of elimination, with zero order, this rate of elimination is independent on the remaining plasma concentration. Meaning, kung ano yung constant kasi yung amount, so wala siyang pakialam kahit ano pa yung natira doon sa plasma or ano pa yung natira na amount of drug. Whereas in the first order, the rate of elimination is dependent on the remaining plasma. So, like 0.12 or 12% lang yung na-eliminate as the previous table have shown us. Now, with regards to half-life, sa zero order, the half-life decreases with decreasing concentration. So, magkaiba yung half-life, no? The half-life is not constant. With the first order, the half-life is constant and independent of the concentration. So, if the drug has a half-life of 4 hours, then we would assume that in every 4 hours, the amount of drug will decrease by 50%. Okay, now, I have a question. Is there an instance when a first order kinetics changes to a zero order kinetics? What do you think is the answer? Well, the answer is yes. There is, or there are instances wherein yung drug, kahit na first order siya, it will change to become a zero order kinetics. Now, when will this happen? What are the instances wherein pwede ito mangyari? There are two most common instances. When a toxic dose is given. So, if we give a toxic dose to a patient, then kahit na first order kinetics pa yung gamot, it will change to become a zero order kinetics or zero order elimination. Another instance is when the enzyme system is saturated. Okay, so these are the two instances that would make a drug change from a first order kinetics to a zero order kinetics. Okay,